Hey, welcome to The Explainer. Today, we're diving into the invisible world of heat and, more importantly, how it moves around. We're going to uncover the secrets behind why some things feel hot, why some feel cold, and how all this energy transfer shapes, well, pretty much everything. Let's get right into it. But first, let's start with a little mystery. Imagine this. You're just sitting in a room, maybe at your desk. You reach out and touch a metal spoon. It feels pretty cold, right? Then you touch a wooden pencil that's been sitting right next to it. It feels, well, normal, room temperature. But here's the crazy part. They've been in the same room for hours. They are exactly the same temperature. So what is going on? Why do they feel so different?
I mean, look at this. It's the same deal. Both of these objects are in the same environment. In physics terms, we'd say they're in thermal equilibrium with the air around them, so logically they should feel the same to us. But they just don't. The answer lies in figuring out how heat actually travels. So stick with me, and by the end of this, you'll know exactly why this happens.
Okay, so to solve our mystery, we first need to get one thing straight. There is a number one, non-negotiable, golden rule of heat energy. It's the one principle that governs everything we're about to talk about.
And here it is, and it's actually super simple. Energy always, and I mean always, flows from a place with a higher temperature to a place with a lower temperature. That's it. It never goes the other way. Your hot tea is giving its energy away to the cooler air, and that same air is giving its energy to your even colder iced coffee. It's a one-way street, always from hot to cold. So, what's the end game? What happens when this flow of energy finally stops? Well, that's what we call thermal equilibrium. It's the point where everything is kind of evened out. The hot tea cools down, the iced coffee warms up, and eventually they both match the room's temperature. Once everything's the same, the energy transfer just stops. That's basically the universe's way of finding its balance.
Okay, so we know heat flows from hot to cold. Got it. But how does it actually make that trip? Well, it turns out heat has three different ways to get around. Three agents of transfer, if you like. So let's meet them. Conduction, convection, and radiation.
First up is conduction. This is heat transferred by touch. Plain and simple. You know when you put a metal spoon into a really hot cup of tea, and after a minute the handle gets hot? That's conduction. The energy is literally being passed along, particle by particle, right through the spoon. And this is our first major clue to solving that mystery from the beginning.
So, let's zoom in a bit. On a microscopic level, how does this actually work? Well, in something like wood, a non-metal, heat makes the particles vibrate like crazy. They start bumping into their neighbors, passing that energy along. It's kind of like a really slow chain reaction. But metals have a secret weapon, free electrons. These little guys aren't locked in place. They can zip all over the place, carrying energy from the hot end to the cold end way, way faster.
So you've got to think of it like this. Those free electrons in metals create a superhighway for heat. While the energy in wood is traveling on a bumpy, winding country road, the energy in metal is blasting down a multi-lane expressway. And that's exactly why we call metals good thermal conductors and things like wood or plastic thermal insulators.
And boom, that brings us right back to our answer. The metal spoon isn't actually colder than the wooden pencil. But because metal is such an amazing conductor, it pulls heat energy away from your warm hand incredibly fast. Your brain feels that rapid loss of heat and interprets it as cold. The wood, being a lousy conductor, sips heat from your hand much more slowly, so it just feels normal. Mystery solved. All right, one down, two to go. Let's move to our next agent of transfer, convection. Now, conduction was all about heat moving through solids by touch. Convection is all about how heat moves in fluids, and that just means liquids and gases, by the actual movement of the stuff itself. The absolute best way to picture this is a pot of water on a stove. The heat at the bottom warms up the water there. That warm water expands, it becomes less dense, and so it rises to the top. When it gets to the surface, it cools down, gets denser, and sinks back to the bottom to get heated all over again. This circular flow is called a convection current, and it's a super effective way to spread heat through the whole pot. And that brings us to our third and final agent, which is a bit of an oddball, radiation. See, unlike conduction or convection, radiation doesn't need any particles or any direct contact to work. It actually transfers energy using electromagnetic waves, and these waves can travel right through the total emptiness of space. The ultimate example of this? The sun. It is 150 million kilometers away from us, with a whole lot of empty space in between. And yet, you can go outside and feel its warmth on your skin. That energy didn't get here by conduction or convection. It traveled as radiation.
making an incredible journey through the vacuum to warm our entire planet.
So let's do a quick recap. Conduction. That's heat transfer by direct contact, and it's best in solids. Convection. That's heat moving around in liquids and gases through currents. And radiation. That's energy sent out as waves, and it doesn't need any stuff to travel through it all. 3 different methods, all doing the same job, moving heat from hot to cold.
Okay, that's the theory. But let's see where these 3 processes actually pop up in the world around you. Because I promise, once you know what you're looking for, you start to see them absolutely everywhere.
Let's take a hairdryer. Electricity runs through a metal coil, that's the heating element, and it gets super hot. The air that's touching that hot coil gets heated up by conduction. Then a fan kicks in and blows all that hot air out. That moving stream of hot air, that's convection. So a simple hairdryer is a perfect little team-up of both conduction and convection.
And convection doesn't just happen in a hairdryer, it happens on a massive scale. Think about the beach on a hot day. The land heats up way faster than the sea. So the air over the land gets hot and rises, and the cooler, denser air from over the ocean rushes in to take its place. We call that a sea breeze, and it's really just a giant natural convection current.
And radiation is, well, it's pretty much essential for our entire planet. The sun's energy radiates to Earth, warming us up. The Earth then radiates some of that energy back out into space. But certain gases in our atmosphere act like a blanket, trapping some of that outgoing radiation and keeping our planet warm enough for life. That's the natural greenhouse effect, and it's a direct application of thermal physics on a planetary scale.
So, there you have it. We've covered the golden rule and its 3 agents of transfer. Let's just take a second to put all the pieces together.
It all boils down to this one core idea. Heat is just energy flowing from a hotter place to a colder place. And we've seen it makes that journey in 3 main ways. Conduction through direct physical contact, convection through the movement of fluids, and radiation through electromagnetic waves. From there, you can trace how each one connects to things we see every day, from a spoon in a cup to the breezes at the beach.
So, I'll leave you with this final thought, a little challenge. Right now, wherever you are, all 3 of these processes are happening around you. The warmth from your phone or computer screen is radiating to your face. The air around a light bulb is heating up and creating tiny convection currents. And if you touch your desk, conduction is happening right there between your hand and the surface. Now that you know the rules of the game, can you see that invisible flow of energy all around you?